Hello and welcome back. So in this series on rigid registration, we are going to look at the image coordinate system. Note that this applies for any kind of image registration. So the general mistake that people would typically make is to actually perform this coordinate transformation that I have been talking about on the index of the images. Like for instance, I comma j is the pixel index or the voxel index, and you typically end up applying the transformation on that, and that is wrong. The problem with that is because when you are considering two different images, even though they are the same patient, they might have different resolution, and the resolution in this sense is actually the spacing between the pixels in terms of a physical distance. So typically all medical images have a resolution defined for them in terms of the field of view and the discretization grid. So every pixel or voxel actually corresponds to a certain physical size. So even though there will be two images which are of the same dimensions in terms of the number of pixels in, let's say, xy direction, if it's 2D images, the spacing between the pixels might be completely different, okay, which corresponds to a different field of view, okay. So before you do any image registration or apply coordinate transforms, we have to do an implicit transform which maps the pixel indices into some physical coordinate space, okay. So this is an implicit transform. You don't have to estimate this, you will have all the parameters necessary to do this, okay. And typically this requires field of view, voxel size, and there's also an origin of the lab coordinate or the imaging system coordinates, okay. So that origin, once you define it, then you're all set to go. So we will look at this slightly more detail with the help of some images. So if you look at this particular illustration here, I have two images, right, with the grid on them, so that it's you understand what we are looking at. 1 second, let me just squeeze them down to manageable size. Okay, I hope these are visible now. So this is, let's say, your fixed image, right? Let's just point this out. This is your fixed image, and this is your moving image, right? And my handwriting is going bad. So this is basically your moving. Okay. So what we want to do is estimate a transformation. But before you have to do the transformation, remember that this, let's say, for instance, I have superimposed a grid on top, but you can always, this is the actual picture here. So if you take a grid somewhere, some pixel in the image, let's say, it's some pixel in the image. I'm going to use black. So this is some pixel, right? This has coordinates I comma j. So this grid represents that coordinates, right? However, underlying this image grid, this I comma j grid, there is a physical coordinate space. It's right here. So what does this correspond to? Here, the spacing between this pixel is given in millimeters. So there is a spacing in x, there is a delta x, and there is a delta y. Typically they are the same. So let's say 1.5 millimeters is a typical spacing between the pixels in medical images. Could be lesser, but this is not surprising, right? So when you come to the moving image, it has its also this has its usual pixel coordinate system, wherein you can also do this indexing. So for instance, this will be this particular pixel here, let's say, could be L comma M or something like that, right? So I've shown this tilted because I'm looking at the same image which has been rotated, okay, and translated, right? So this is this is a rigid transformation. So but associated with this picture is another underlying physical coordinate system, okay. So what you have to do is, in order to apply, so if you want to figure out what this pixel corresponds to here, let's say you have the transformation ready, all you have to do is from here to there. So I comma j to some x comma y you have to figure out using a one transformation, and from here to a corresponding pixel, let's say here somewhere. This is the t that you are going to apply. Okay, so this transformation is applied to the x, transformed from ij to xy, and from here you are going to have to estimate one more transformation that takes you, sorry, I got the wrong thing, that takes you, let's say, right there. Okay, so there are these implicit, these are two of the implicit transformations. Now these can be done if you know the parameters of the imaging system. So for instance, the field of view, some scanner fixed coordinates are usually given, and with respect to the scanner fixed coordinates, the xy positions of the images are typically known. So is the z if we are considering a 3D image. Okay, so using that you have to figure out the transformations and not operate on the indices of the image, because of this problem, not problem, because of the fact that the medical image is actually, the pixels mean something in terms of dimensions. Okay, both along x, y and z direction there is size of the pixel, that is the extent it occupies, as well as the spacing between the pixels. So you have to understand you have to know what the spacing between the pixels is in order to go from ij to x comma y, and then from after doing the transformation to the moving image, figure out what its indices are. Okay, so here also this is where interpolation comes, right? So once you figure out this x comma y, when you apply a transformation matrix, it won't land on a grid. I have shown it landing on somewhere on a grid, but it may land on not on a grid point but an off grid point, right? Because these transformations operate on real numbers. So then what you have to do is, then you have to do interpolation in order to figure out the value of the intensity. So if you want to know the intensity value at a particular location that you are mapped into, you have to do interpolation from the original image. Okay, so that for that also you need the physical coordinates rather than working with the indices. Now there are some cases you can work directly with the indices, like I said, if they are the same modality, same patient or the same field of view or the same scene, and it's the same resolution, same everything, everything else in terms of the origin of coordinates, etc. Okay, so then this is an issue. So here there are few things that you have to map, right? You have to know the origin of these coordinates, right, of these coordinate systems. Like maybe here, this is, it's always 0 0. Origin of these coordinate systems you have to know, right, before you can. And you also have to know these pixel dimensions for both your moving and fixed image. So that this distance, now if you want to zoom in and show you, usually if I zoom it, the thing goes to the dock. So the pixel dimension is basically between the distance between the center point of the pixels, let's say, right here. In this case, if you go from here to there, yeah. So this is the distance. This is typically your what you would, let me go back to the original picture, right? So yeah, so that's the distance that you want to know, that you will know based, because the image in the scanner will have it calibrated and you should be able to estimate that. So what is that transformation, these implicit transforms that we are talking about? What is it? How do we do that? So the way to do that, let me just write it down quickly. So this x prime, we want to go to, in this case, this is a vector, I write it as x prime, y prime. So you are going from the index to the coordinate, you have this dx 0 0 dy times I comma j. So this is your pixel index. There's a plus ox oy. So this I comma j is your pixel index. That's typically how you would access the elements in an image array. So this dx dy are basically your pixel spacing. Okay, typically these are in millimeters, right? And finally you have the ox and oy. Sorry, my d and o might look slightly same, but ox and oy, this is basically your origin of coordinates. This is in 2D. You can write similarly for 3D also. Typically, we will work in 2D in a lot of cases, right? So, how do you, like I said, where do you get these values from? Sometimes they may not be available. Then you have to get creative about how you fix the origin, etc. So, for instance, you can always fix the origin at the bottom left pixel or the top left pixel of the image and things of that sort. But these values are expected to be available to you from the scanner itself, right? So once you do this, so once you have your ij, you transform to this x prime, xy, you apply your transformation to that. So your transformation matrix should be applied to your coordinates, not to ij. So this is not done. So I'll do this in red so that you know. You don't apply to ij but rather xy. And then once you, from here, then you will get a new set of x prime, y prime. Okay, because after the transformation, now you have to convert this back into in pixel indices. Again, you can just have to invert this transform to do the same. Okay, so this is something that is always coming up in image registration. So hopefully I've addressed this problem. Once again, just to reiterate, all medical images have a finite pixel sizes, where there is a dimension to the pixels. They cover a certain area or volume in your body. So there is its pixel spacing is in millimeters. There is actually the origin of coordinates is available in the sense where is the 0, 0 for the physical coordinates. It's there. It's there for both the mixed as well as the moving images. So all your transformations will be applied to those physical coordinates, and you will convert them into the indices using this transformation I showed you, provide that you know the pixel spacing as well as you know the origin of the coordinates. This can be done trivially. Okay, so this is a calculation. You don't estimate dx, dy or yxy, right? You just fix them. So that's typically how it's done. Okay, so for the next few lectures we will look at different types of transformations that are available and different types of metrics, basically intensity based metrics that are used for image registration.